I'm Roland Minton. These are some of my favorite math stories. In this episode, Mathematics is the Mandelbrot set. This is part one of a two-part series where we explore the Mandelbrot set, one of the most remarkable objects in mathematics. We'll need to develop here some skill with complex numbers, but the payoff is in some beautiful pictures and amazing facts. The Mandelbrot set is named for the mathematician Benoit Mandelbrot, who in 1982 published a highly innovative and influential book giving the name to and popularizing fractals. Although there is no universally accepted definition of fractal, the concept of self-similarity is a fundamental property of many fractals. We have seen the Sierpinski triangle in other episodes. You can see miniature copies of the triangle within the triangle. This is self-similarity. To understand the Mandelbrot set, you need some facility with complex numbers. These are numbers of the form a plus bi. A and b are regular, real numbers, and I is the square root of -1. So 2 plus 3i and 4 plus 5i are complex numbers. Graphically, we associate the complex number a plus bi with the two-dimensional point ab. We also need the concept of iteration seen in other episodes. To iterate x squared, for example, start with some number x, square it, take that value and square it, take that value and square it, and keep squaring the answers. Two examples would be 2, 4, 16, 256, and so on, where the iterates blow up to infinity, and 0.5, 0.25, 0.0625, and so on, where the iterates converge to 0. How do you do arithmetic with complex numbers? Well, it's the same as with real numbers. If you add 2 plus 3i and 4 plus 5i, you can rearrange, put the two real numbers together, 2 plus 4 is 6, the two i's together, 3i plus 5i is 8i. Multiplying 2 plus 3i times 4 plus 5i, you FOIL it out, 2 times 4, 2 times 5i, 3i times 4, 3i times 5i. In that last term, you've got I times I. We're going to assume that I times I is -1. Since I is the square root of -1, that makes sense. So we have 8 and a -15 at the end, making -7. 10 plus 12i is 22i. So here's how the Mandelbrot set is defined. For any point AB, form the complex number c, a plus bi, and then iterate the function f of x equals x squared plus c starting at 0. If the iterates blow up, p is not in the Mandelbrot set. If the iterates do not blow up, p is in the Mandelbrot set. Well, that doesn't sound too bad, but you definitely want a fast computer to do the work for you. There is a nice shortcut for the set. If any iterate reaches a magnitude of 2, and technically magnitude is the square root of a squared plus b squared, the iterates definitely blow up. And this gives us a coloring scheme for the picture. The color for points not in the Mandelbrot set is determined by how many iterates it takes for the magnitude to pass 2. Here's a basic picture. In this case, the Mandelbrot set is in black, with lighter oranges and yellows and greens corresponding to larger numbers of iterates to get past 2. Part of the magic of the set is that it has infinite detail with colorful spirals and near copies of the set within the set. This image is from a deep zoom into the set. Google Mandelbrot zoom and you can find some spectacular videos zooming into the Mandelbrot set. Here are some captures from a zoom sequence that goes into the lower crack and finds various spirals and then a miniature Mandelbrot to start the zoom all over again. We'll see some amazing properties of the Mandelbrot set in part 2 of this episode. For now, we'll look at a very strange occurrence. In this image, it appears that the portions of the Mandelbrot set, this time in blue, in the regions 1 and 2 are tangent and touch each other at a single point. This is in fact true, and the point is the complex number -0.75 plus 0i. Now, how do we know that they only touch at one point? Moving a little bit straight up or down from that point would move us from -0.750 to -0.75y for some small number y. If -0.75y is not in the Mandelbrot set, then the iterates of f of x equals x squared minus 0.75 plus yi, starting at x equals 0, should become larger than 2. When we use y equals 1/10, it takes 32 iterates to pass 2. When y is 100, it takes 314 iterates. When y is 1,000, it takes 3,142 iterates. Do you see a pattern to this? Well, here's some more data for you. You might know that pi equals 3.1415926 and so on. Yep, the number of iterates needed to pass a magnitude of 2 is creating the digits of pi. I love that fact. If you want to know more about the Mandelbrot set, including what the numbers 1, 2, 3, and so on in that graphic mean, watch part 2.